Why do people go bald?
Why are baboons' bums red?
What's a light year? Why do leaves go brown in the autumn? Why do monkeys like bananas? Why do some things glow in the dark? Why do animals not understand you? Why do my receipts fade after a year?
Don't know the answer? Ask the Naked Scientists.
Hello and welcome to this week's Ask the Naked Scientist with me, Sue Marchant, and Chris Smith. What have you got happening?
Well, there's a nice story I saw recently. Spider silk.
Spider silk, yes.
Yeah, it's really incredible stuff. Just normally, it's actually stronger than steel. It's 2 or 3 times stronger than mild steel, and even 30% stronger than the really high tensile, very strong sort of spring steels.
Really?
Yeah. So these spiders are really bright things. And it's not just it's stronger than steel. The real thing it's wonderful at is absorbing energy. So because it can stretch, it's very strong and it's really stretchy. So it can absorb more energy even than Kevlar. So sort of maybe 10 times more than Kevlar.
Right.
So they want to use it for things like bulletproof vests. Because if something's moving very fast towards you, it can, if you just have something steel or Kevlar, it might snap and break. Whereas the spider silk will bend and stretch and stretch and stretch and not break.
Right.
But some German scientists thought this isn't really good enough. We should try and make it even better. So what they've done is they've been firing zinc, various metals at bits of spider silk and seeing what happens to it. So they've been sort of firing little metal atoms of zinc, aluminium and titanium at it, and they've found that it comes out even stronger. They've got it so it's 3 or 4 times stronger than it was before, so far stronger than steel. And maybe up to 10 times tougher than it was originally, with especially they use titanium metal. So you can make spider silk's incredible stuff, but you can actually make it even better with an application of a few metals.
I wonder how the spiders feel about that.
Yeah, there is a big problem that if you ever want to use spider silk in major quantities, you need so many spiders it will become entirely impractical.
Exactly, there'll be spider farms.
So I think they're giving up and they're trying to make it in all sorts of things. Like they're trying to make engineer goats so they can make spider silk for you and all some old bacteria. So basically they're trying
engineer goats?
Yes. So some people were trying to make goats so as their milk would produce, not silk so it came out in lines, but the proteins which you can then make the silk out of.
Sounds like one scary experiment to me. It really does. Let's start with our first question tonight. Andrew in Cambridge says, question for you, Dr. Dave. What is it about the electronic and physical structure of titanium dioxide which makes it such a brilliant white pigment?
Titanium dioxide itself, if you got a big crystal out of it, I think it's just a clear crystal. It's got quite a high refractive index. That means that light goes quite a lot slower in titanium dioxide than in air, and even slower than it would be doing things like glass. So that when light hits it at an angle, it will bend, it will refract through quite a large angle. Also, titanium dioxide comes in very, very small particles. Now, if you imagine a piece of glass, if you've got a piece of glass, if you look at it, what colour is it, see? It's clear, isn't it?
Yeah.
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 But if you imagine taking that piece of glass and then smashing it into lots of small bits and then grinding those bits up, what ground glass starts to look white?
Yeah, white and sort of snowy, doesn't it?
Yeah, sort of snowy. It's because all of the individual particles of the glass are still transparent. It's just because there's lots and lots of surfaces there. When light hits them, it either reflects off them or it refracts. And so it keeps bouncing around. And so if it comes in one direction, it'll come out in a random direction. So all the colours of the rainbow coming down and hitting it, they all get mixed up. You mix up all the colours of the rainbow, something looks white. I think titanium dioxide just happens to come in very, very small particles. And it's got a fairly high refractive index, so it will bend the light a lot and you get lots of reflections. So it's very easy to get hold of it in very small particles. And so the light comes from all directions, bounces around and comes out. You need a very, very thin layer of it to cause light to have bounced off several particles. So you get a lovely white paint.
There's nothing worse, is though, than getting a bit of paint and think, oh, just touch up that mark there, and it's a totally different colour from what you got. There we go. Anyway, thank you very much for that question. Let's go to our next one. Alan in Orpington. I always thought I was allergic to cat's fur. However, I was recently informed that it's not the fur but the cat's spittle, which is what they leave behind after they've cleaned themselves. Then it becomes airborne, and that's what causes the allergic reaction. Is this true? I've never heard of that one. Thanks, Alan, for that.
I think he is right. I mean, allergies are complicated, and certainly the most common cat allergy is one to a protein called FeL-D1. This most cats make both in their spit and also in their sebaceous glands. These are the glands which produce the oil, which sort of essentially conditions the cat's hair.
Yeah.
And also the cat, because it spends a lot of its time cleaning its fur, it puts spit onto its fur. And then, yes, it'll dry out, and it'll as soon as it dries out, it forms small particles and will blow around and blow into your nose. Your body takes exception to this and starts trying getting rid of it, so you start sneezing and generally feeling unpleasant.
I think I'm allergic to my mother's cat. Now, from cat allergies to swine flu. Agnes in Braintree says, a question about swine flu. Why is it called swine flu, and does it have anything to do with pigs?
Chris is probably the expert on this, but I can certainly say something. It's called swine flu because the closest flu we know of to it is a flu which was going around pigs in North America, so sort of America, Canada, Mexico. It itself, the fact it was most recently in pigs, it's made up of various, as far as the scientists can see, by taking the flu apart and looking at the proteins inside, it seems to be made up of bits of older swine flus, older pig flus, some bits of human flu, and some bits of bird flu as well. Basically, because flu can be caught by various different animals, sort of birds, humans, and other mammals, and sometimes it can jump between different animals. If you've got two flus if you're a creature and you've got two different types of flu at the same time, sometimes they can get a bit mixed up. So I think probably in pigs somewhere in North America, a few other flus got mixed up. It's produced a particularly virulent, particularly successful flu. And now, although I'm not sure whether pigs can actually catch the what we're calling swine flu at the moment. Yeah. But certainly most people are catching it from other people, not from pigs. So it's not, as far as people know that I've heard, there's no worry about pig meat at all. It's just it originally came from pigs. Flus do this all the time. They jump between different animals. And because if there's been a flu that's been around for a long time, most people have become immune to it. Yeah. So it's not so successful. It's the ones which have jumped from other animals, which humans haven't had for a long time. Sure. That we're not very immune to. So then everyone will catch it.
Not very pleasant either. All right, let's go to our next one. This comes from Mike, who says, concrete. Is it true when it was invented? It was invented by the Romans. And how do people get it a quarter of a mile in the sky when building skyscrapers without it setting?
Yes, I mean, the Romans certainly used concrete. As far as I know, the Romans invented it, or someone in Italy invented it. I think there was actually a volcano where somewhere in Italy where essentially concrete came out of the ground pretty much as Portland cement came out of the ground as Portland cement, so they didn't have to try very hard to get the idea. And then after they worked out how the volcano was making the cement, then they worked out how to make it themselves. And yeah, there's lots of Roman buildings. It's part of the reason why they've lasted so long, because they're made out of a good strong concrete. Things like there's a beautiful building in Rome called the Pantheon, I think. See, the Pantheon of the Parthenon. My Latin's not perfect, which is actually the roof is a dome. And the dome is made out of cast concrete in a very sort of modern you almost think the design is almost a 60s sort of cast concrete dome, but the Romans were doing it sort of 16, 17, 1800 years ago.
Fantastic.
And how they get it up and down tall skyscrapers, I can't say I have direct knowledge of this. I mean, I would have thought, concrete, as long as you keep stirring it, and it's perfectly. I mean, they drive it around in trucks.
Yeah, I mean they do it in sections at a time, don't they?
I mean, it can last for hours. So I'd have thought they use a big crane if it is starting to set without it being stirred. I guess you could have a hopper on the end of a crane with some stirring motor on it if you need it. With a fast crane, you could probably get concrete up a skyscraper relatively quickly.
Yeah. Yeah, it is a sort of Scrabble thing, isn't it? If you're laying a piece of concrete down for a garage base or something, it's like, until the cat walks across it or something. This one comes from Val in Clacton. It's all about slugs. Funny little creatures. In the daytime, you find a slug in under something in the garden. It tries to go back somewhere in the dark. So if it was to stay dark all day, how does the slug know that it's night time?
I don't have any specific evidence on slugs. It's certainly not my area of expertise. I can make a few guesses. One of them is that just daylight is incredibly, incredibly bright. If you've ever been in a room which is lit by daylight and then you turn the lights on, although if it was nighttime you turn the lights on, it makes the room feel incredibly bright. If it's during the daylight, it hardly makes any difference at all. It's because sunlight is incredibly strong, and even if the sun's in under clouds, daylight is very, very strong. So the slug might be able to see little bits of light, sort of little chinks of light getting in through to where it is, which is really quite dark, but it might get even darker at night time. The other thing it can probably detect is temperature and humidity. When the sun goes in, it gets dark, the temperature is going to drop, the humidity is going to rise, and the slugs, once the temperature gets cold, once it gets cold and damp enough, the slug's probably going to come out. Because actually, in fact, I wouldn't surprise me if that was the reason, because during the day you sometimes get slugs coming out if it's very wet. So they're probably essentially just waiting for it to be damp enough and cool enough for them to be happy, and so they don't dry up too quickly.
Yes, they can slide across in the way, and it's just awful if you tread on one by mistake, isn't it? Now, Dr. Dave, Keith has asked, how vast is space? Does it come to an end or keep going, in your opinion? It's my spacey music. Okay. How far? The first question is, how far can we see? How big do we know the universe is? We can see out to about 13 billion light years. So that's light has been travelling for 13 billion years to get to us. Light travels at 300,000 kilometres every second. So that's an awful long way. Yeah.
We know the universe has expanded a lot in that time. And so if the furthest thing we can see at the moment, if you then work out how far away that must be now, if the whole of the universe has expanded at a constant rate, that must be about 60 billion light years away. Beyond that, you start getting into the realms of cosmology, of very. You haven't got a lot of evidence. You're in the realms of kind of speculation.
Cosmic.
There are various theories. There are people have considered the fact that the universe is a bit like a sphere, a bit like the Earth, but in more dimensions. So if you're in any direction for long enough, you'll get back to where you started. I don't know that this is completely ruled out. I think there is some cosmology which indicates it's probably unlikely. But to be honest, on that scale, there are lots of things we don't understand. There's this big problem called dark matter, which essentially means that astronomers don't really understand, cosmologists don't really understand the way the universe works on really big scales. Yeah. And they've invented things which might solve that problem. We don't know if it exists. It might just be that we don't understand how gravity works on large scales. So beyond that, I don't know.
If you're enjoying Ask the Naked Scientist, then you might like to check out The Naked Scientist, our regular roundup of the world's best science. Each week we take a look at the latest science news, talk to top researchers working at the coalface of discovery, and also get our hands dirty with a science experiment that you can join in with too. So make it a date and prepare to strip down science on the web at nakedscientist.com/podcast. Now, let's get to our next question. Where have we got to? Let's click forward up here. Gillian Ipswich was just hearing us talk about spiders. She can't stand them, but she has watched them and she does find them fascinating. And she says, why is she so scared of spiders?
In this country, it seems like a very strange thing to be scared about, because virtually all the spiders in the UK aren't going to do you very much harm. None of them are particularly poisonous. I think one of them might hurt a little bit if it manages to bite you, but none of them are actually going to do you any serious harm. So it seems a very strange thing to be scared of. In other countries where we have evolved, sort of Africa, there are lots of quite nasty sort of creepy crawlies which are really quite poisonous and could do you a lot of harm. So it sort of certainly makes sense that you would be aware of small creepy crawly things which might bite you and do you a lot of damage.
Yeah, I think it goes back to these programmes you used to watch as a child when you're having your tea and suddenly they'd have these big insects, which were only small really, but the camera work was fantastic on them. And they used to be like climbing up and sort of almost getting in your dinner as you're watching TV. And you used to think, oh no, because they just, they look like little monsters really, but they're not, they're quite happy things. But yeah, I'm not the biggest fan of fairy spiders.
I think there's certainly I think it would make sense. I haven't looked into this, so I don't have any evidence that it would make sense for you to be sort of a bit aware of kind of creepy crawly things which might be poisonous. I don't know whether I have a feeling that the spider thing might be that sort of a general awareness of creepy crawly things, and then associated with that sort of a cultural thing. Yeah. Because if your parents are scared of something, it'd be a good thing for you to be scared of it, because there's probably a reason why their parents are scared of it. So it's better for you to mimic them than discover that actually it was poisonous and you die. So I think it's probably a mixture of cultural effects and a general tendency to be aware of creepy crawly things.
Keith says, talking of spider steel for bulletproof things, years ago he had an aluminium-lined suit. How cosmic is that, Keith? Supposedly to keep the heat in and the cold out. Would it be a good thing to still make these?
Using aluminium as an insulation material first seems quite strange, because actually aluminium is a very, very good conductor of heat. Yeah. If you grab hold of one end of an aluminium bar, if the other end's hot, this end's going to be hot. The reason why they do it is aluminium is also a very good material to make mirrors out of. And quite a lot of heat is transferred by radiation. If you have a hot electric fire and you put your hands near it, you can sort of feel the heat coming off it. That's actually a form of light called infrared light, which is beyond the red end of the spectrum. If you look at a rainbow, it's quite the heat which is coming off a bar is quite a long way off the red end of the spectrum. And this is what you feel. And if you put a mirror near light, the light's going to bounce off the mirror and go somewhere else and not heat up the mirror. So if you have a shiny piece of aluminium in your suit, then any radiative heat radiation which hits it is going to bounce off and not heat you up. So it acts as a very good form of insulation. There's some modern housing insulation which uses this. You have lots and lots of layers of plastic covered in a very, very thin layer of aluminium, so it makes a nice mirror, with thin layers of glass fibre in between, with sort of 10 or 15 layers of this. You can get a form of insulation which is as good as maybe 6 or 8 inches of rock wool. So, yes, I mean, they definitely use it for the sort of emergency blankets as well. The ones you see people putting on at the end of sort of the London Marathon and things. Yeah. So, I mean, it's certainly a principle. I don't know whether people do use it. I would be surprised if they don't use it at all. For very hot fires.
Be quite shiny, wouldn't it? I might like something like that. Now, John in Peterborough says, in the Victorian times, they used to run mills by steam. One steam engine used to run 50 looms. How efficient was that in comparison to running the same amount of looms that you would probably use today with electricity?
There are a couple of reasons why they don't do it, and one of them is certainly efficient. One of them is the fact that it was generally lethal. You had all these huge belts flying around the factory, and small children used to get trapped in them and killed and lose arms, fingers, legs. It was a horrible place to work, I think. And the other one was efficiency. For a start, steam engines, particularly the old ones, were horribly, horribly inefficient. I don't have any figures in my head, but I mean, sort of at least a tenth as efficient as a modern car engine, and certainly at least a tenth as efficient as a modern power station. So that was, you're throwing away coal. At the beginning, they weren't very well insulated. They ran at very low temperatures, and the higher the temperature you run a steam engine, the more efficient it is. And so that was horribly inefficient. And also, moving energy around mechanically isn't very efficient. You're losing energy at all of the joints. You're losing energy pulling belts around and bending belts and stretching belts, and all of the bearings are getting hot, slightly warmer and warmer, if you keep them really well oiled. So that's not very efficient. Electricity is actually remarkably efficient. If you've got a well-designed motor, it can be over 90% efficient, so you're only maybe losing 10% of the energy you're putting in. Same with a generator. And if you transmit it well, you can lose less 5% of the energy. So I would have thought that electricity there's a reason why people use electricity. One of them is much more convenient, much safer, and the other one is it is a lot more efficient.
Here's a good question from Kev in Great Yarmouth. Absolute zero is represented by the complete cessation of movement in an atom. If heat can be shown as an indication of the speed at which the atoms are moving, and nothing can move faster than the speed of light, then heat too must have its limits. Ooh, Dr. Dave, if so, then what?
Slightly more subtle. Heat is actually a measure, or temperature anyway, is a measure of the energy, essentially the energy per atom. It's a little bit more subtle than that, but the energy per atom in a material. The hotter it is, the more energy each atom's got. An absolute zero is a temperature at which you can't take any more energy out of a system. Actually, because of quantum mechanics, it doesn't mean that everything has stopped moving. Because in some senses, an electron, even if you can't take any more energy out of it, it still has to be going around the atom for it not to fall in. And so it's still got some energy, but you can't get that energy out. It's locked in there. So absolute zero is when you've taken all the energy you can out of a material thermally, and it can't get any colder. As to maximum temperatures, although there is a speed limit, there isn't an energy limit. In fact, the reason why you can't go faster than the speed of light is that to take something with mass and make it go at the speed of light, you need an infinite amount of energy. Every time, if you get slightly closer, if you're getting 99% of the speed of light, you need a ridiculous amount of energy. To get the next 0.5%, you need far more energy than you needed to get to 99% of the speed of light. And to get that next halfway there, you'd need more energy than you needed before. And so to actually get there, you need an infinite amount of energy. And because temperature is a measure of the amount of energy per atom, that means that you can still keep getting hotter and hotter and hotter forever because you're putting more and more energy in, even if the particles can never go faster than the speed of light.
Dr. Dave, I'm sat here looking at him with an intelligent look on my face in wonderment here. He's such a bright chap. Now, is it possible, Dr. Dave, asked Mike, to reverse gravity, i.e. gravity pulls upwards?
Depending on your definition of gravity pulling upwards, if in some senses, if you go to Australia, compared to here, then gravity's pulling upwards, because it's pulling in the opposite direction to here. But we sort of define downwards as the direction which gravity's pulling in, so it's almost always pulling downwards. If you mean, is it possible to make gravity so it repels? Because at the moment, as far as we know, anything with mass attracts anything else with mass, and everything else with mass. So all the bits of the Earth attract each other and pull it into a sphere. As far as we know, no. No one's found anything which has a repulsive form of gravity.
So, no. Thank you very much for that question. Bob in Essex has asked, what is the actual speed of electricity? Also, if you were to send a pulse of electricity and then turn it off, would the original pulse travel the end?
To the end. Okay, what's the speed of electricity? It depends slightly on the material you're using, and in fact there's different ways of interpreting this. One of them is electricity is a flow of electrons, and one interpretation is how fast those electrons moving. And if you look at a copper wire in the ceiling, they're actually only moving at millimetres per second. They're moving very, very slowly through the material. But because all the electrons repel each other, if you've got a big long wire, you've got full of electrons essentially, and if you push an extra electron in at one end, then that push, imagine a whole row of balls. If you push one ball at one end, each ball is going to push the next one, the next one, the next one, the next one, the next one. So even though all the balls are moving very slowly, the pulse which you put in by putting a ball in will travel all the way along the row of balls very quickly. So if you put extra electrons in at one end, then that movement is going to get transferred down the wire, depending on nearly the speed of light, sort of between half 0.7 the speed of light, something on that, again, depending exactly on the material. So that's very, very quick. If you put in a pulse very quickly at one end, then that pulse, you'll get a wave travelling down the wire.
Right.
If you start having pulses moving very, very quickly in sort of millions of times a second, billions of times a second, then you've got to be very careful of this effect. And essentially, you get waves travelling down the wire, and you've got to design everything to take into account this.
Lastly, Keith says, in the Bible, why was copper more precious than gold? It's a long time ago.
It's a very long time ago. Similarly, in South America, copper was more certainly more precious than copper. It's to do with how useful it is. I mean, gold, to be honest, actually isn't very useful for very much. It's only actually had any real uses in the last 50, 60 years because it's so unreactive.
Teeth.
Teeth it's been useful for because it doesn't react with anything and it will stay there for a long time. And also for covering contacts because it's so very, very unreactive. It doesn't get oxidised. You also get a lovely electric contact all the time. So gold is only really valuable because it's pretty and because it doesn't rust and so it stays pretty. It doesn't oxidise. So intrinsically gold isn't very valuable. It's just rare, so people think it's valuable. So if you're actually interested in doing something with your metal, and especially if you have a gold mine nearby and you have quite a lot of gold kicking about, then some useful metal is going to be more valuable. Copper's harder than gold. You can make better weapons out of it. You can make better axes out of it, especially if you mix it with tin. If you mix copper and tin, you get bronze, which is quite a good metal, not as good as steel. Similarly, something which I noticed when I was reading the Iliad,
yes,
which is the story of I think it was either the Iliad or the Odyssey. Iliad, I think possibly the Odyssey, with Odysseus getting back from the siege of Troy, written by Homer, sort of 600 or 700 BC. I think it's written down 600 or 700 BC. It's probably an older story than that. And one really fascinating thing is that there's one bit of it whereby someone was giving someone a present to another king, and there were cauldrons of silver and cauldrons of gold, and even cauldrons of iron.
Iron.
So iron was the way it was written, that iron was far more valuable than gold.
Wow.
And it's because at that time there wasn't very much iron. It was a very difficult thing to make because they hadn't really got the technology sorted.
That's it for this week. Our doctors will be back with me next week for more Ask the Naked Scientist. But don't forget, you can also catch them on the Naked Scientist podcast, which you can find on the Naked Scientist website, www.nakedscientist.com.
The Naked Scientists are sponsored by the Wellcome Trust, the EPSRC and UK Fast. For more information, look us up online at nakedscientists.com.